My name is Camilo Fosco, and I'll be presenting our paper, We Have So Much in Common, Modeling Semantic Relational Set Abstractions in Videos. What do these videos have in common? What is the general concept that connects them? Humans can easily recognize that these videos all depict some form of competing. Machine learning models, however, still struggle at inferring these abstract connections. In this work, we introduce a framework to model these common concepts or abstractions between sets of videos. Our model combines visual features as input with natural language and classification supervision to generate high-level representations of the abstract concept relating the inputs. These representations allow us to solve tasks such as set completion, where we try to find a video that best completes a given set, and odd one out detection, where we try to find the video that doesn't belong in a set. As we focus on the relationships between events in sets of videos, we leverage large video datasets depicting varied events such as kinetics 400 and multi-moments in time. Although these datasets contain action labels for each video, they don't explicitly indicate how these action classes relate to each other and how they could be grouped into more general concepts. To obtain this information, we build a graph connecting each action class to a more general concept according to the WordNet lexical database. We additionally augment the ground truth information in the graph with NLP word embeddings of each action class and each general concept. We call the resulting organization a semantic relational graph. Our semantic relational graph is based on the WordNet lexical database, as we said, a graph that groups words into cognitive synonyms or synsets and interlinks them based on their semantic and lexical relations. Importantly, this allows us to define abstractions for classes through their hypernames. We use WordNet to build the initial graph that is then augmented with semantic embeddings by computing fast text representations for each node in the graph. The process to build the DAG is as follows. For each dataset, we match each action class to a synset in the lexical database, which captures the specific meaning of the action itself. We then extract hypername paths for each of these classes and add the members of these paths to our graph. For example, in this case, we add the synset windsurf to our graph to match the class windsurfing from kinetics. We then add surf as a parent of windsurf, glide as a parent of surf, and so on, following the WordNet hypername paths. The resulting graph links every action class to increasingly general concepts. There is high variation in numbers of children and grandchildren, and nodes can have multiple parents, making this a directed acyclic graph. With this graph, we can easily define abstractions linking any set of videos by finding the first common ancestor of their action classes. In this case, the common abstraction between an instance of dust and an instance of rinse would be clean. If the videos share multiple parents, we obtain a set of abstract concepts instead of a single one, and prediction becomes multi-class classification problem. Each node in the graph is additionally assigned a 300-dimensional semantic embedding based on the subword information skip graph model, also known as fast text. We first assign fast text embeddings to the leaf nodes and then compute for each parent the average of the children's embeddings, as well as the embedding of the parent's name. This ensures that our semantic embeddings stay close to the features of their children and also capture language-based information of the parent concept. Once this process is complete, we obtain the semantic relational graph, a directed acyclic graph connecting each action class to increasingly general concepts and containing semantic embeddings at each node that provide additional language-based information on the concept that the node represents. Armed with this graph, we build training and testing datasets for abstraction tasks. As we work with sets of videos instead of individual instances, we collect datasets by sampling varied sets of videos from the graph. To do this, we iterate over each parent class in the graph and randomly subsample n videos belonging to any descendant. We assign a ground truth label to that set corresponding to the lowest common ancestor of the video classes sampled. The ground truth label contains both the classification target and the semantic embedding targets. We use this setup to obtain 1 million video sets for training and 500,000 for testing from the kinetics dataset. For multi-moments in time, we sample 5 million sets for training and 100K for testing. With the dataset at hand, we're ready to train a model to understand set abstractions. We introduced a semantic relational abstraction model, a model that produces a vectorized representation of the abstraction connecting a set of input videos. Our model first utilizes a 3D-based network to extract visual features. It then feeds these representations to a set abstraction module that computes intermediate representations from combinations of the initial features. And finally, the intermediate representations are combined to build the final abstraction representation for the set of input videos. The intermediate and final representations are supervised with semantic classification losses. To be more specific, we applied 2 types of supervision at each of the 3 stages of our model. The initial visual representations are mapped into 300-dimensional vectors and that are then used to compute MSE loss with the NLP embeddings. Additionally, the representations are used to produce action class predictions where a cross-entropy loss is used. In the second stage of the model, the representations computed for combinations of previous ones are again contrasted with NLP embeddings from corresponding parents in the graph. We additionally train these intermediate representations to predict the parents of the video classes in each subset. And finally, at the output of the model, both loss types are again utilized, ensuring that the final vectorized representation has sufficient predictive power and that it approximates the semantic embedding of the desired abstraction. The main task that our model performs is classifying the abstraction that links a given set of videos. We show some examples here. Our trained model can directly predict high-level abstract concepts and surpasses previous work when compared to several baselines. The model can pinpoint relationships between very different actors, inanimate objects, and even different types of video, such as cartoon versus film. In terms of qualitative results, our model shows good performance in predicting abstractions and individual action classes. We show the predictions for individual videos at the bottom and the predictions for abstractions at the top. The ground truth is shown in brackets. As can be seen, our model is able to understand that videos picturing very different cleaning actions all depict some form of cleaning. The ability to understand abstractions even when given videos with very different actors and scenes is observable across examples in both datasets. When compared to several baselines, our model outperforms all alternatives, including relational networks or closest previous work. The second main task that our model solves is set completion. Given a reference set and a set of query videos, our model can select the query that best fits in the reference set. The model ranks the query videos according to how similar they are to the abstract concept of the reference set and selects the closest video as the set completion. To compare our model performance to human performance on this task, we developed a simple Amazon Mechanical Turk task where users are requested to rank 5 query videos according to how close they are to the general concept depicted by a set of 2 to 4 references. The responses collected were consistent according to split half consistency analysis, which ensures good data quality. Again, in terms of quantitative results, our model outperforms baselines and comparable models, and gets close to the human baseline in several cases. Finally, we use the abstraction representations to find videos that don't fit in a given set. Our model does this by extracting the abstraction representations of all videos but one and calculating how far the left out video is from the abstraction. Here, our model easily detects that the unplugging video is most different from the rest. In the example with 3 videos, the rotating actions are identified as more closely related than the barking video. In terms of qualitative results, again, our model surpasses baselines and performs comparatively to humans, particularly in kinetics. The model is good at picking the odd one out in kinetics' fine-grained human-centric actions. In conclusion, our proposed framework allows us to design and train a model that is able to predict representations of abstractions between events. We can then use those representations to solve several cognitive tasks, such as completing a set or finding the odd one out. In the future, we will test our framework in few and zero-shot learning tasks, leveraging our representations to categorize unseen videos by measuring their distance to different abstract concepts. We will also explore more general types of abstractions that explicitly take into account objects, actors, and scenes. And this will bring us one step closer to free-form human-like abstraction abilities, the final goal of this project. For more, please see our paper and website. Thank you for your time.